All right. So how many of you ever have heard of a mass spectrometer? Okay. So now you know how one works. Basically, one needs to ionize molecules, generally in a gas, ionize so that they're charged, so they have a charge, electrical charge Q, either positive or negative, and then those, I call them slow moving, because if they're in a gas, they're moving at low speed, whatever the thermal motion of the gas is at room temperature. Those ions are accelerated across two plates. So these two plates here are at different potentials, different electric potential. Ideally, you would use something like, so in homework you had, I think it was in homework, you had a velocity selector where you had magnetic fields and electric fields both. And what that produced was a bunch of particles that were moving at the same velocity. So if you accelerate particles with two plates at different potentials, and you select for a particular velocity, then what you end up with is a stream of particles coming into the mass spectrometer, and you put a magnetic field on them, and then they come around and they run into a detector. So how is this a spectrometer? A spectrometer is something that picks out different, well, usually I think of spectrometers as things that pick out different energies, or different wavelengths of light or something, but this is a mass spectrometer that picks out different masses. So how does that do that? Well, there's a magnetic force here. If you remember, the magnetic force depends on the ionic charge, the velocity vector, and B. And so the magnetic force is always perpendicular to the velocity. So the particles don't speed up in a magnetic field. In fact, a force that's always perpendicular to the velocity is a force that takes things and pulls them around in a circle. A force that's always perpendicular to the velocity vector this way, acceleration vector that way, or maybe down here, velocity vector, tangent to the curve, and acceleration vector toward the center. That's a centripetal acceleration. Centripetal just means center-seeking. So it's an acceleration vector that points toward the center. Why is that point toward the center? Because the magnetic force is perpendicular to the velocity, and so it points toward the center of the circle. If you remember from 9a, the centripetal acceleration depends on the mass of the ion, the square of the speed, and it's inversely proportional to the radius of the circle. So that's from 9a. Also from 9a, that better equal the net force, and the net force is just the ionic charge times V times B. And so this gives you an equation for R. This is Newton's second law. You can solve this for R, and you find out that it's related to the mass of the ion divided by the charge of the ion. So a charge to mass to charge ratio, or the reverse. one of the V's cancels, so where am I? I got V over B. If I've used a velocity selector, then all of the ions have the same velocity. They all sit in the same magnetic field. And so the ones with the larger mass have a larger radius. Strictly speaking, the larger mass to charge ratio. You might try to ionize to make all your ions singly charged, but that's not trivial. When you ionize something, you add a bunch of energy, and sometimes the ions are +1 charge, and sometimes +2, and sometimes -1, and sometimes -2. So you can't always control the charge very easily. But what you do is separate out ions that have different mass to charge ratio. You just put a bank of detectors up here, and ions with this value of R run into that detector, and you count those up. Ions with a larger value of R run into a detector over here, and you count those up. The larger value of R just means larger mass, basically. Got to worry about the charge, but if we presume they all have, if we take them all to have the same charge, then the ones with the larger mass will be over here, the ones with the smallest mass will be over there, and we have built a spectrometer, something that separates and counts how many of each mass there are. Yeah?
How can you guarantee they're all the same velocity if they have different masses?
So you cannot if you just accelerate.
Okay.
So you could do, I would suggest a good thing to do would be to use this velocity selector. I don't remember if you remember how we can select for velocities. You can select for velocities by having, suppose you have a bunch of particles coming through a constant electric field, then they have a force upward. And if you give an equal opposite force downward, so the magnetic, how would you get a magnetic force downward? If they're positively charged, then they'll have an electric force upward. If they're positively charged and moving to the right, then you need a magnetic, I think a B field pointing out will give you a magnetic force downward for positive charges. And if you, so the magnetic force equals the electric force. If that's true, then the particles go straight through. You put up a block to let only the ones that the two forces cancel go straight through. The two forces can only cancel if the velocity is just right. If the velocity is too big, then the magnetic force will be bigger. And if the velocity is too small, the magnetic force will be smaller. So it's at least possible. There may be trickier ways of doing this, but it's a pretty straightforward way to make sure that you have all the same velocity. Any questions about, this is mostly not about a mass spectrometer, but about this magnetic force law and the fact that particles in a magnetic field circle around or have a acceleration that brings them around in a circle. The circle is perpendicular to the magnetic field because the magnetic force, because it's this V cross B, the magnetic force is always perpendicular to the magnetic field. By the way, if you had a magnetic field like the Earth's field right now points basically north right here, so points in this direction. If you have a particle that is moving downward, then it'll circle around the magnetic field. But if a particle is moving in some other direction, of course, if it's moving directly north, there won't be a force on it at all. Magnetic field is north. If it's moving in some other direction, then the force on it is still perpendicular to the magnetic field, and so what it ends up doing is spiraling around the magnetic field. So it keeps going in the direction of the magnetic field with no force in the direction of the magnetic field, but a force that causes it to go around as it moves that way. So helical motion of particles in magnetic field is actually fairly common. You have to set up exactly the right geometry to make sure that there's only that kind of motion right there.